Go ahead.
Thank you very much, Patrick. So today we're going to deal with sound, and we'll learn how to make beautiful noises like that and deal with harmonics. So today, I want you to write this down. This is your learning objective today. This is what we're going to accomplish. You're going to experimentally calculate the speed at which sound travels in propane, which is not normally the medium that we are in.
Are you sure?
Yes, as it turns out. So go ahead and write this down. Does anyone know how fast sound moves in regular air?
43 meters per second.
Very good. How fast does it move in space?
Doesn't. You trickster, Sean.
Trick question.
Not a trick question. It's the same answer as any. Just different than most. Let's do a quick review of some of the things we've been looking at. So remember, waves interact constructively and deconstructively. They interact with each other. So if I start one pulse, then another pulse, when they meet, they're going to interact with each other. Here they are both going, they both have the same direction of amplitude, so they're going to interact constructively, meaning they're going to add together. Whoa. When they're moving in opposite directions, they will interact deconstructively. You see, they cancel each other out. Very good. And then if I do an oscillation, you'll see that when the waves come back and reflect backwards, they're going to keep interacting with these waves coming this way. And then what is produced is a what?
Standing wave.
Very good, a standing wave. So remember we did this with this fun little giant slinky. Beautiful. Today what we're going to be doing with is a little bit different. So we're dealing with sound waves. So sound waves are longitudinal rather than transverse. So you're still going to get the same standing waves, same type of standing waves, but the way that they propagate is a little different. So this is a little visual of this. So this is regular transverse. Whoops. Start. That'd be a regular transverse. But if I'm doing longitudinal, it's more like this. So you still have points. So, around here where's your node where it's not moving, that will still be a node. You see it's still not moving back and forth. And still your points that were moving up and down the most, those are still your points that are moving side to side the most. So it's very similar to transverse, but just a little different. Transverse. Woo. Today what we're dealing with is sound waves, longitudinal. And specifically what we're dealing with are sound waves in a tube, a closed tube, or stopped end. So, I believe we've all looked at these. So this is all review. Your first harmonic or first fundamental frequency in a closed tube. Remember we can only have a first, a third, and a fifth, a seventh, odd numbers. So these are the way that the waves will look, the sound waves. And you can see inversely, the pressure is a little bit different. The pressure is opposite, which will show you a good visual of this here soon. So that's how a transverse wave would look in these tubes. Here's how it actually looks, you know, when the air molecules are propagating through these longitudinal waves. So you can see you have your sound wave, and where you have the antinodes, that's where the most movement is. But in the same sense, when you have these nodes, that's where your greatest pressure is. That's where all the air is pushing together. And when we're dealing with the Rubens tube, which I think you're all familiar with and you've been looking at and eyeing up for the last couple of days, that's where we're actually going to see the waves forming, the peaks forming from these pressures. But when you note, it's not going to affect our calculations too much, because for every, you know, if you have two nodes in a tube, you also have two antinodes. So what we're looking at is the same number of peaks and valleys. All right, well, I think we're about ready to get started with this. I'd like you to do one thing for me first, and that is together in groups, maybe pairs, pair-group groups. I'd like you to draw the first 6 harmonics that you can have in a closed pipe. So draw those visuals for me. And those were so basically I want these drawings, but for the first 6 harmonics that you can have in a closed tube. Thank you. All right, so I'm going to come around and check, make sure you guys are getting these. Excellent job so far. Yeah. Yep. You got it. First one. So you have an opening, and then you're going to need another. So it's going to need to be a node here at this base, and antinode here. Yeah. So very good. You got it. So draw one, and draw this one. So you know that's one. And then look here, so you can stop there. So that's your first one. Does that make sense? Okay, so that's your third. And then the next one, you can have one more of these. So that would be your fifth. So this would be your third. Because it needs to start with the closed and then with the open. So here's the first one. That's the first one. And the next time you can do that is here. Next time after that, you can do that is here. And then one more would be there. So you're very good. Awesome. Yeah, and these are difficult to do once you get up to 6. You get a lot of circles in there. But we're going to have a lot of peaks in our actual tube. So I want you to start visualizing them now. First time you can do those two. Open. And close. So the first one you can do that. The second one you can do it. So if you were to keep doing this, here's your first one. Here's your second. Yeah. Your third. Fourth. They are, because if you multiply this frequency, this fundamental frequency by 3, you get this. Technically, yeah, but it's not right now. Exactly. Oh, excellent. Yes, yeah. Very nice. Yes. That's the first one. That's the first one. Yeah. Second one, that's the first one. Here's the second, here's the third. So you can see the frequencies. You know, this frequency, this is 3 times. This is 1, 2. It's just the next time you do it.
Pretty sure it's because of
Also, this is your close one. Yeah, very good. These are awesome. Very nice. Oh, excellent. Very nice. Would someone like to come and draw their beautiful? These are nice.
I actually did these. I did these ones and you did those ones.
Would you like to draw these up there?
I would-
Which ones?
What? Hey, you guys. Do you want to, or if you don't, he wants to.
Patrick.
Patrick wants to. Patrick, come on up.
do I have to draw?
Let's draw the first 6. Let me.
Can I just draw a little bit? That's my best one.
Did you enjoy yours?
Yeah.
If they're right, yeah, I'll draw.
So you need to look at this one. So here's your next one that you draw. That would be 3.
Oh, okay.
Okay, so that's 5. That's 5.
Oh, okay, I see. Okay, got it.
Let me while you're doing it. And then just stretch it out. That's the length that is. So here's the first time you now closed, open, like, and watch it out. So I mean, you could always go for it. Let me take a look. Because you're not closed. Because I just, you want
That's the first thing you can see.
I'll draw the first one.
Didn't get much easier. I guess that's
Okay.
There's something there's 2 more. We need to should have been.
They're not. This is actually 7.
Alright, so you guys.
Just they couldn't have him in the movie because of Jack. He's slightly as far as
I don't think you pressed the button.
Yeah, don't press it.
yeah, we're talking about in the comics.
Ian's gonna draw these for us. So it looks like most of you guys are getting these very well. A few of you still have troubles. But I think we're gonna work that out right now. So
If you basically follow this, you could keep going. Okay, here's the first one where it's really close, but he has a check as soon as here's the second time. Here's the third time.
Yeah. So yeah, just don't freak out. It's all right. You're good. All right, let's see how he's doing. I wasn't paying attention. Is he doing all right?
Yeah.
Except that fifth one got a little messed up.
That looks pretty nice to me.
No, the fifth one's right.
They get tough to do after a while.
He doesn't.
Ian's pretty good with that marker, or that pen.
He is. He should be a teacher someday. Excellent job. Excellent job. Warm round of applause. All right, so these look very good to me. Let's label these though as harmonics. So let's try someone else. Neil, which harmonic is this?
Number one.
You got it.
Yeah.
All right, Kayla, which one is this?
3.
3. Very good.
No, it's 3.
Chad, how about this one?
5.
You got it. Okay, let's really throw you off. Which one's this? Christian?
7.
Why do you think it's 7?
It was just a guess too.
Oh, well, you shouldn't have guesses, so we need something to support your guesses. So, this one is 1. Calm down. 1, 3, 5. And then you keep going on the progression. You can see that the wavelength here, so this is a third of this. So really, this frequency keeps increasing by, this is 3 times the frequency of this. This is 5 times the frequency of this, assuming they're the same length, 2. So, maybe this is an easier question, Christian. Which one is this? Oh.
7. Oh.
You're right. Go ahead, say it. 7. So, why do you feel that this is the 7th one? What's some criteria that you would choose?
Well, I'm kind of noticing a pattern with because the ways they form those ovals.
Yeah.
The third one,
So here's your antinodes and here's your nodes.
the fifth one has 3. The third one has 1.
Okay, so your first one has 3 of these open spots. And this one has 1, 2, you're saying.
Yeah.
So you keep seeing them progress, and then this one has 4 is what you're saying, so it's the next one up.
Yeah.
And you're seeing how these numbers increase. So you're just seeing the pattern here?
Yeah.
Okay. So you're right, this one is the 7th. I'll take that as a pretty valid answer. Also, you can see that this frequency is 7 times greater than this fundamental one. So each of these blocks, I'll go ahead and draw them on here. So this is one of these. 2, 3, 4, 5, 6, 7. So this is 7 times the frequency of this one. You see that? And the wavelength is 1/7 of it. I gave you the hardest one. All right, so now this one. Vaughn.
9.
9. Very good. And who wants to help me out with this one? Peyton?
11.
11. Very good. Christian, does that help? Excellent. All right, any questions on these? You guys ready to watch me play with fire?
Yes.
Fair enough.
Let's let
Made you wait way too long. All right, so here's the Rubens tube. I created this with a former student many years ago. But the general idea is you have a propane tank, filled with propane. That's where the propane's coming from. It's filling this up. We have a diaphragm here, which I just used a latex glove and a zip tie on. We have speakers. Remember, speakers are just going the same as, and that will vibrate this diaphragm and cause the vibrations, the longitudinal vibrations. So, just want to let a little bit in. A little less. All right, excellent. And now, when I'm putting different frequencies through here, you'll start to see how these waves interact in the tube, how the pressure systems are going to cause the fire to do different things. So let's get through. And I'll just start going through here. This is a nice little iPod app. You can have it home. It's going to be tough to tell what's going on until we get to some of the higher ones here. So you can see it starting to form there. You can see the sound waves. Can you stream a little bit more?
Put 'em out.
You see these are the waves there.
Holy cow.
Standing waves like that. So that's cool. So let's count how many this is. 1, 2, 3, 4, 5, 6, 7. And then I want you to write down the frequency for this one. This one is 765 hertz. So write down when you have 7,
What was it?
765 hertz. And then we're going to keep going down. So doing this, we're going to be able to figure out our fundamental frequency. I know you guys like this frequency, but I'm going to go down a little bit. Here's our next one. We see we have 1, 2, 3, 4, 5, 6. And this frequency is this one's 660 hertz. Record that. All right, going down, going down. That one looks pretty good. 1, 2, 3, 4, 5. And this frequency is 560 hertz. There we go. Really say 1, 2, 3, 4 for this one. And this one is 460 hertz. See it a little bit better there. We're going to give this one a 3. 1, 2, 3. We'll say this one is. And this one's 355 hertz. They start being a little bit harder to recognize further down, so those are the ones that we're going to use. How many people can hear that? That's officially the lowest threshold of human hearing, 20 hertz.
Lower.
The app doesn't, unfortunately. I feel like it's probably not maybe completely accurate because I could hear it really well.
Yeah.
My hearing is not great.
Uh-huh.
So let's go back over there. We'll figure this out a little bit, and then later on, when there's a little bit of time at the end of the period, we're going to relate, a couple of you guys brought your instruments in, we're going to relate how harmonics work when you're playing your instruments. Filming in. You guys are working on these. There's something I want you guys to recognize. So, for example, when we had 5, standing waves, 5s, what we saw was antinodes. Which one would this correspond to? So let's take a look at this, and let's not shout it out, but look, which one do you think would produce 5, high arcs in the frequency? So go ahead and raise your hand, and I'll call on you. Luke.
11.
11. Very good. So we can see 1, 2, 3, 4, 5. It's going to be 5 arcs. And this is the open end, which we're not really going to see from that. If we want to get technical, they're from the high pressure systems, which are from these nodes being compressed. So 1, 2, 3, 4, 5 also. Let's extend a little bit further. So right, you're exactly right. So something you're going to need to know for this is the length of this tube, which was 1.2 meters. So now I'd like for you guys kind of work in pairs, see if you can figure out the average fundamental frequency. So it's going to vary based on, we got different numbers for each harmonic, each different harmonic, 11, 9, 7. You're going to have to look at each harmonic and say, well, which one were we looking at? And figure out the fundamental frequency based on that. You're going to take the average of those fundamental frequencies, and then from there, see if we can find the speed of sound in propane. And maybe it'll work, maybe it's difficult. It's not a completely accurate setup, but we'll see how we do. I think we'll do probably all right. So go ahead and get started on that. See if I can do these as well as Ethan.
Speed of sound 7 is number.
So we're solving for B, right?
Yeah.
No.
It's getting a little light in here. And I've taken the liberty to draw some of the higher ones for you. So you can see the number of nodes and antinodes in the 13th, 15th, and 17th harmonic as well.
No, that's the hertz. That's the frequency.
Yeah.
So these aren't 3 seconds. I thought N is on.
Oh, no. Okay, so for this, this is how many peaks there were, right? So it's how many peaks there are. 1, 2, 3, 4, 5. So this one is 6. 1, 2, 4, 5, 6.
There's 6.
Oh yeah, okay, so this is 1, 2, 3, 4, So if you have 6, then it's the 13th.
And what's my velocity?
So this is the 13th harmonic. That's what we're trying to find eventually. The velocity of the sound is. Yeah.
So you have.
And then hours. Sorry about that.
You guys are doing excellent so far. I'm really happy to see you guys all getting this.
Okay, so yeah, this isn't just because there's 7 peaks, doesn't mean it's the 7th harmonic. So which of these has 7 peaks? And this isn't 6. This is yeah, so go ahead and make
To find the average.
Excellent. So let's look at one that has 5, right?
What's your
So which one of these has 5?
245 plus or minus 1.
It's 244. Add all the got together.
So you can see there also. 45.
Oh, yeah,
So that's what. And then yeah, everything else is right.
244.3.
How you guys doing?
Oh, that's one.
So I'm going to give you a few more minutes. For those groups that feel you're done, I want you to get together with the groups next to you and kind of collaborate, compare answers. I don't want you to argue why the other person's wrong. I want you to argue why you are correct. So use valid science, equations, and explain to the other groups why you are correct. Yes?
You have the same. And you got the same.
Good. And if you have the same, maybe just verify why you guys both feel you're correct.
We got 298.
Okay, we're
Pretty close.
okay, so then 400
Yeah.
compared to everybody else.
You see why?
Yeah, just because the wrong number.
Yeah, exactly. You got it? Reasoning as well.
You're getting great.
Huh?
You're getting great.
I'm old. What happens? You get gray. All right, so let's bring it back towards the front. How's that look? Whoops. There we go. So let's review your procedures. Most of you guys look like you're doing this very well. The equation for the frequency in a closed or stopped pipe is Fn, this being the number of harmonics, equals n, the fundamental frequency, times n, velocity of the sound, over 4, the length of the tube. So, when we had, say, 5 peaks, that would be due to 5 pressure points. So, we saw 1, 2, 3, 4, 5. So when it's 5 peaks, it's not the 5th harmonic, which a lot of you guys recognized. It is the 11th harmonic when you see that. So for the one where we saw 5 peaks, you would put 11 in for this. The frequency we had when we had 5 peaks, and then that would give us our fundamental frequency, which you guys all seem to be doing very well. And since we're limited on time here today, I'm not going to go over too much. So you all did that very well. Let's try one example. What was, for the one with 5 peaks, what was the frequency? 560 hertz? Very good. That is the 11th fundamental, 11th harmonic. So the fundamental frequency would be 560 divided by 11. So the fundamental frequency here would be
50.9.
So is that
50.9.
50.9. What's my units for this? What's my unit for frequency?
Hertz.
Oh, hertz.
Hertz, right? Hertz, don't it? All right, so 50.9 hertz. Excellent. And then also, so you guys did a very good job of calculating this as well. So for the first fundamental frequency, we put 1 in for n. Okay, great. We're looking for our velocity, 4 times our length, which was 1.2 meters. So our 1's not a big issue. We're going to multiply 50.9 hertz by 40 times 1.2, and that will give us our velocity.
244.4. Yeah.
We did it. Velocity equals.
44.4.
Neil Perkaiser, please come to the main office. Neil Perkaiser, please come to
Neil.
the main office.
No, that's 244.
244, I apologize. And let's stick with 3 significant digits right now. What's my units for this? Meters per second. We know that because that's velocity. But also, let's look at the dimensional analysis. Hertz. I mean, it's hard to say what hertz is, but hertz is number of waves per seconds, right? So the unit for that is 1 over second. And we are multiplying it by meters. Meters times 1 over second is meters per second. So these units all need to work out. Remember that. If your units don't work out, probably the problem's not going to also. 244. What is the accepted value of the speed of sound in propane? I believe I have it written over here.
53.
253. That's pretty good. Okay, so we saw that we were a little off. And also, since there was fire, I'm sure that propane was a little bit warmer than normal. So probably the speed of sound is even more than that in propane. But that's pretty good. I think that's a really good job. I think you guys did an excellent job today. And the bell's about to ring here. I thank you very much. And have a great day.